So this is Unit 1, Lesson 4 for AP Calculus. The unit is called Limits and Continuity. The lesson is called Estimating Limit Values from Tables. In this lesson, we're going to learn how to evaluate a limit from a table of x and f of x values. And we're going to learn about when x approaches infinity and negative infinity and what that looks like in a table and how to evaluate that. So consider the limit as x approaches 5 of this function right here. We can look at it graphically. As x approaches 5, as x equals 5, we have f of a would be undefined. And we know that's true, but looking at the equation, if x equals 5, if we plug in direct substitution, then we see that we get 0 as a denominator. So on our graph, that yields just undefined. And there it is. 5 is undefined. We see that over here. F of a is undefined. So now if we want to look at as f approaches a from the left, we can make a super close to 5 but not be equal to 5, or we can go from the right and make a greater than 5, approach 5 but not equal 5. So if we use this graphing tool, we can come up with some estimates. So as x approaches 5, we can kind of build a table. We can look at x equals 4.5, 4.9, 4.99. And if we play with these values, 4.5, we get a y value of 0.169. If x is 4.9, we get a y value of 0.167. 4.99 gives us 0.167, which is the same as before. And so if we keep adding 9s, I notice that our y value kind of hit its limit, 0.167. So as x approaches 5 from the left, our limit is 0.167. From the right, we can plug in 5.5, 5.1, 5.01. For our a value, 5.5, our output is 0.164. 5.1 is 0.166. 5.01, 0.167. And if I keep making that interval shorter and shorter, I see that as we approach 5 from the right, our limit is about 0.167 as well. So on this function, even though at x equals 5 we're undefined, as x approaches 5 from the left and from the right, the limit is 0.167. So in class, I filled in the green here on this table and asked you to use your calculator to find the y values. And so we can find the limit as x approaches -8 from the left and from the right. And if we go from the left, we see that the x values are steadily going up to about 1.5. If we go from the right, so fun fact, this came up in class, -7.5 is to the right of -8. Remember, negative numbers are kind of backwards from the way we normally think of them. As we approach -8 from the right, we notice that our outputs are going down towards 1.5. Now, I made a separate video. The question came up, how can I use my graphing calculator to do this table efficiently? So check OneNote, find the link for how to use your graphing calculator to build tables and work with them. And that'll make this task way easier for you. So anyways, looking at this table, we find that as x approaches -8 of our function from the left and from the right, it's equal to 1.5. Let's look at some examples here. So here's a table with the x values and their outputs. As x approaches 2 from the left, the symbol right here, 2 with a kind of a superscript of a minus sign means 2 from the left. As we approach 2 from the left, we notice that our x values approach -3.5. Excuse me, -3. -3.5 goes down to -3.05, which goes down to -3.005. So we're going up to -3 on the left. the limit as x approaches 2 from the right. As we go from the right 2.1 and work our way towards 2, our outputs go from negative 2.5, negative 2.95, negative 2.9995. We can see that from the right, we're going down to negative 3. So the limit as x approaches 2 from the right is also negative 3. And since the left and the right both approach negative 3, the limit as x approaches 2 is also negative 3. However, f at the value of 2, if we evaluate f of 2, it is undefined. And we just know that because it says so in the table. So another example, in this case, we'll see what happens when the left and the right don't equal. As we approach x equals 2 from the left, our x values approach 2, but are less than 2. Our y values go from 2.8, and it jumps up to 3.4, and then it goes back down to 1.5. And then as we approach 2, we get 0. So now, even if I don't even consider the 0, as we get closer to 2, we go up and we go down a lot more than we originally were at 1.9. And so because there's no consistent pattern here, and because we're not really given enough information, enough data points to really figure out what's going on left here. It's going up, it's going down, and then eventually it's 0. Or is 0 just like, a hole somewhere? We don't have enough information to conclude what this is. So based on this table, we must conclude that the limit as x approaches 2 from the left does not exist. As x approaches 2 from the right, we see that our outputs do have a trend, 5.21, 5.021, 5.002. As we approach 2 from the right, our limit is positive 5. As we approach the limit as x approaches 2 of g of x, since the left side and the right side don't agree, they're not the same thing, then we'll just say our limit as x approaches 2 does not exist. And our table tells us that g at 2 is equal to 0. So now about what it looks like when the limit approaches infinity. So as we look at as x approaches 2 from the left, we get a y value as from 1.9 to 1.99. We're jumping by 9 hundredths, but the output goes up 100-fold. And then from 1.99 to 1.999, we're going up by only a tenth of what we went up by before. This interval is a tenth of the size of the first interval, going up by 9 hundredths, 9 thousandths, excuse me. So even though we're going up by a tenth of the interval as we did before, we're still going up by, our outputs are still going up by over 100-fold. And so what we're seeing here is a trend that the outputs doesn't seem to be approaching a limit. The numbers just continue to get even greater and even greater. So this tells us that the limit as x is approaching 2 from the left, the limit is going to approach infinity. As we approach 2 from the right, we see a similar trend, 0.8. We go up by a fraction of 1/100th, or sorry, yeah, that's 9/10 down to 2. It goes up 100-fold. And if we go by even a tenth of a factor, it's going up from 80 to 1,000. So another 100-fold. We can see that we're not reaching any stable limit. The number just keeps growing crazy fast. So the limit as x approaches 2 from the right is also infinity. Therefore, the limit as x approaches 2 is infinity because the left and the right both agree. And the table tells us that j of 2 is undefined. Now, if the question says, how about the limit as x approaches negative infinity, or the limit as x approaches infinity? So if we want to read a table to find the answer to these limits, what we're going to do is just going to throw in really big numbers. So for the limit as x approaches negative infinity, throw in a really big negative number. And then a bigger one and a bigger one and a bigger one. And we're trying to see if we can find a pattern. As we approach negative infinity, we can see that there really isn't a pattern going on. We got positive 0.4, negative 0.3, positive 1, negative 1.1, positive 0.87. There's no pattern here. So based on this table, we don't really have enough information to find the limit, or the limit just doesn't exist. So DNE. As we approach the limit, as x approaches infinity on the positive, we can just put really big positive numbers in here and bigger, and we can see that the outputs are reaching a limit. They're kind of flattening out at about 1/2 or 0.5. So we can say the limit as x approaches infinity of f of x equals 1/2 or 0.5. Takeaways for this lesson. We can use tables to explore functions and estimate limits, but do keep in mind this is only an estimate. In the next lesson, we'll get to more concrete evaluations of limits. And also, we know that infinity is pretty cool.